Good night, everyone. Right? Welcome to Appet's Mechanical Division fifth technical webinar session for the year. More than likely, unfortunately, might be our last until probably next year, January. Uh, Today we'll be doing a very informative session on shaft alignment on horizontal machines or horizontal rotating equipment, of a very popular topic amongst mechanical engineers. So before we start, I would just like to go through a few chat room etiquette or how we will run today's session, right? First of all, if if you all could put your first names and last names within the name column, so I would know how to address you all, right? We will try to avoid any nicknames, right? Just for just for professionality's sake, right? Uh, During this session, if you could keep all mics on mute, there would be a question and answer session after after the technical presentation is done. And at that point, you are free to talk, right? If you do have questions that you don't want to unmute and speak for, you could type it in the chat section. All that is welcomed. We entertain that. You feel free to turn on your mics. All that is entertained. And 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 yeah, just take your notes and listen and learn. Have some fun. Before we start today, I would just like to give a brief safety toolbox or a brief safety session, right? Seeing that we're going to talk about rotating equipment and the corrective known as laser alignment or shaft alignment. Uh, for those of you guys who are seasoned in plants, right? It is good practice if you are going to do a corrective like shaft alignment that you ensure that you adhere to your company's lockout and tagout procedures. That could well save your life with procedures like shaft alignment, field balancing. Anything where you have to interact with the rotating element of your asset, ensure that you adhere to your lockout and tagout procedures. Very critical. Next one. Uh, when you are energizing your machinery, keep your hands away from all rotating any rotating part, especially shafts. Right. So do not breach any machinery guards. That's bad practice. That's not safe. Right. So once your machinery is energized, do not breach any guards. Right. Uh, Also, when you are starting up your equipment after the alignment procedure, right, it's good practice to keep a good distance away from the projectile region of your machine, just in case, because during startups and shutdowns, that's when most torsional forces are, are present, torsional resonances, there's a possibility you could have a failure, right? You don't want to be within that projectile zone. So you should stand clear of the projectile range of the rotating equipment. Uh, During the alignment procedure, it's good practice or safe practice to wear the right PPE. So when you're handling shims, wear your cut resistant gloves. When you're handling your wrenches, your torque wrenches, your spanners, it's good to wear impact gloves so that you keep your hands safe just in case you have any pinch points or slips while there's manual handling of your tools and stuff. So all that is good practice. So that's my safety section with regards to rotating, well, shaft alignment and safety with regards to shaft alignment. And without further ado, I will introduce Mr. Engineer Lyndon Vidal, right? I've had the privilege of knowing Lyndon for over 10 years, just over 10 years, right? Lyndon is an engineering professional with approximately 20 years experience, and 13 of those years is with respect to reliability and condition monitoring, right? He is, I want to get this one right. He is professionally registered with the Engineering Council of UK as an incorporated engineer, an ING, right? He holds his Category 3 vibration analysis certification, which is very rare in the country. He is trained and competent with shaft alignment, all the techniques regarding it. He is a certified machinery lubrication engineer from the International Council of Machinery Lubrication. He also holds certifications and is competent in technologies like motion amplification, electrical signature analysis, ultrasound. So, in a nutshell, Lyndon is the right person to deliver this technical session, right? So, without further ado, right, I will give Lyndon the floor and let him take it away. Lyndon.
Thanks, Leston, engineer Leston, for that introduction. It's make me feel special here.
Hey, no problem.
So
You deserve it.
everyone seeing my screen?
10-4, positive. I am.
Yeah,
Yes, it louder.
Nice. So the title of this webinar is An Introduction to Shaft Alignment of Horizontal Rotating Machines. So of course, it wouldn't be possible to detail everything on shaft alignment with the time period we have here. Normally that is at least a 3-day course. Just let you know that last week I was speaking with a fellow professional and I told him I had this presentation to do for APET. And he asked me which pet was it? Was it the dog or the cat? So, but I can confirm that no animals were harmed during the production of this PowerPoint presentation. So our agenda for today we'll be looking at introduction. You define misalignment. We look at tolerances, and we'll also look at evaluating misalignment. All that in the introduction. We'll consider the question why align, then symptoms of misalignment, diagnosing shaft misalignment, pre-alignment checks, methods of shaft alignment, and then we'll conclude with a case study. Nothing too difficult. So to begin, the theme is an introduction to shaft alignment of horizontal rotating machines. So this is what we're talking about. Horizontally oriented pairs of shafts supported by pairs of bearings. So basically 2 machines with 2 bearings. For example, as the image shows, a motor to a pump, or a motor to a fan. The power is transmitted from one shaft to the other by a flexible coupling. So it's a direct drive. So we're not talking about through a gearbox. We're talking about a direct drive. So misalignment, what is it? Well, misalignment is the deviation of the relative shaft position from a collinear axis of rotation measured at the points of power transmission when equipment is running at normal operating conditions. So that's a mouthful, right? So what you're talking about, the position of the shafts, they should be as one line of one axis of rotation. So that's where the expression collinear axis of rotation comes in. The points of power transmission, you'll see that shortly. And then when equipment is running at normal operating conditions. So when it's at normal operating conditions, we want the machinery to have collinear or a single axis of rotation, single line axis of rotation. So in a horizontally mounted drivetrain, two of these deviations occur in the top view, describing the amount of side-to-side or lateral misalignment. So we look at our image to the right. We see the bottom pair of images. We see the horizontal angularity and the horizontal offset. So note the machine feet. Note the machine feet. The view is from on top. So looking at a plan view. So that's the horizontal. The angle, the coupling is open, so you have a gap there. And then the offset is parallel to each other. So that's the horizontal. And then the top, we have the vertical angularity and the vertical offset. Note the machine feet. So this is looking at the machine train from the side view. So horizontal, we look at the top or plan view. And vertical, we're looking at the machinery train at the side at end view or end elevation. So that's the two more deviations occur when the drivetrain is in the side. So we just discussed that, right? We talk about the points of power transmission. What is that? Well, rotational power from one shaft is transferred over to the other shaft through flexing points. The flexing points are the points of power transmission. So shaft alignment accuracy should be independent of the type of coupling used. Some persons say that, the coupling could take the misalignment. But shaft alignment accuracy really is independent of the type of coupling used. It is a function of the shaft positions, not the coupling design or the mechanical flexing limits of the coupling. So looking at our image to the right, we see different types of couplings. And note the flexing points, right? So the flexing points, we have the tire, we have the chain, we have the wood type. That's the top three coupling inserts. Then we have the shim pack or this type coupling on the bottom. We have the gear, and then we have the cardan shaft. So these flex points are the points of power transmission. Why should misalignment be measured at the flexing points of the coupling? Well, it is where the coupling accommodates the misalignment condition and where the forces, wear, and power transfer across the coupling is occurring. So that's the reason why we should measure misalignment at the flexing points, is where the forces, where the power transfer across the coupling is occurring. So how do we evaluate shaft alignment? Well, there are two methods to do so. One is the offset and angularity between the shaft center lines to indicate alignment. So this is probably the most popular way of evaluating shaft alignment. So the offset describes that the center lines of the axes that are not collinear but parallel. And the angular describes the center lines of the axes that are not parallel. So looking at our first image on the right, we see the offset, the arrow pointing up and down. So it's parallel. And then the angle, so it is meeting not parallel. Note that shaft alignment systems don't actually measure angle. What you measure is the rise divided by the run. So that is where we get the angle from. And with offset and angularity, looking at the center point of the coupling. So that's one way of evaluating shaft to shaft alignment. The other way is to two coupling faces relative, the offset at each of two coupling faces relative to the distance between them, yielding a pair of angles described in mils of offset per inches of separation. So mils per inch, or tau per inch, as we say locally here in Trinidad, or micron per millimeter. And that's what the image, the second image to the right shows. So you see the two flexing points and the angles, angle A and angle B. So this way of evaluating alignment is what is typically used, for example, in cooling tower alignment, where you have a motor with a long spacer shaft to a 90-degree gearbox turning a fan. So this is the type of alignment that we typically use in that situation. So slide show. Right. So let's talk about tolerances now. Prior to the year 2017, tolerance tables from various shaft alignment system manufacturers were used without consensus. Usually, these tables give shaft alignment, offset, and angularity values common for common machine speeds. Spacer coupling tolerances are expressed as the limits to the angle that may exist between each machine shaft and the spacer piece between them. It is specified as the maximum angle allowed between the spacer shaft and each of the connected machine shafts. In 2017, ANSI and ASA, that's the American Acoustical Society, they released a shaft alignment standard, Part 1, which deals with general principles, methods, practices, and tolerances. It was revised in 2020.
Lyndon?
Yeah.
With regards to that slide, we're not seeing it. You have to select it on your end.
Oh, okay. Sorry.
Yeah, no problem. Yeah.
Stop share. You see, stop share. Let me reshare. Are you seeing my screen now?
Yeah, I'm seeing it now.
Positive. Yeah, see it.
All right, nice.
Thanks.
All right, yes, right. So sorry about that. So we have two tolerance tables here. The bottom table first, this is actually from the ANSI standard, where they have the tolerance range. You have minimal, standard, and precision. We have various speeds, RPM. We have 900, 1200, 1800, and 3600. The offset in microns and mils, and then the angle. So this is what we'll utilize for offset and angularity, or short flex. Sometimes some persons utilize that too, short flex couplings. Looking at the table on top, you see it has the offset, the gap, which is the angle, as well as the spacer shaft. And note the spacer shaft is only mils per inch, which is the angle, right? So that's what we highlighted before. There are two ways of evaluating shaft to shaft alignment, either the offset and angularity, short flex, or the spacer shaft, which is just concerned with the angle and not necessarily the offset between the pair of shafts. Right, so why align? Well, according to a survey of attendees at the International maintenance conference in 2012 on the most recurrent machinery failures, misalignment stands out in first place, or within the uncertainty margin of the survey, it's within the top 3. So looking at this pie chart here, we see misalignment 32%, unbalance 18%, bearing failure 31%, looseness 16%, and others 3%. So misalignment is a bugbear for maintenance engineers, craft persons in the plant. So if it's not the top cause of machine failures, is among the top 3. So that's why alignment deserves special attention at our facility. So why align? Well, correctly, align shafts mean many improvements. It means increased machine availability. And once you have availability, we are able to make product and we're able to sell that product and bring in money, revenue. So you need a machine running to do that. So correctly aligned shafts mean increased machine availability. It also means increased service life of bearings and seals. So you have to stock up less on these, less leakage and a better working environment. You know, leakage among pumps can present a slip hazard. So you don't want those working around the equipment to be injured based on leakage from seals. Less risk of overheating and secondary damage, less lubricant consumption, less vibration, reduced noise level, less risk of serious breakdowns, and greater overall savings with fewer spare parts, lower energy consumption, and less unscheduled downtime. So these are some 9 areas why we should consider aligning our rotating machines. Symptoms of misalignment. Well, we have premature failure of a bearing, bearings, seals, the shaft, or the coupling, excessive radial and axial vibration, high housing temperature near the bearings or high discharge oil temperature, excessive amount of oil leakage at bearing seals, and loose foundation screws or false support. Right, so these are some symptoms, and you see it illustrated here in this little graphic. The machine vibrating, you have bearing damage, you have coupling failure. You notice at the bottom of the coupling, you're seeing filings of the coupling, and then you have seal wear, right, which results in leakage. How do we diagnose shaft misalignment? Well, the number one way really is through measuring it with a shaft alignment system. And number 2 will be vibration. For those trained in vibration, you have the wall chart where you have like 1x and 2x as typical symptoms of shaft misalignment. So that's for the wall chart. In reality, is a little more different than that. Based on the type of flexible coupling insert, you can see 3x, 4x. So it all depends on the coupling insert actually. And when taking phase readings across the coupling, even though you may see 180 degrees plus or minus 30 degrees, which is typically used to confirm misalignment. As we saw before with the tolerances, there was no zero tolerance. So the thing is, whilst with phase you may be able to discern that there's some misalignment, the thing is it within tolerance? So vibration may not be able to tell you that. You have tomography, as the image shows, you're looking at the bearing areas, and you could note the heat signature, and if it's excessive, and then oil analysis. Well, you won't see a misalignment in oil per se, but you'll see wear particles in the oil, which could lead to a diagnosis of misalignment. So some pre-alignment checks. We look at the general conditions, the temperature, vibration, pipe connections, the mounting bolts, and the coupling. So these are, you just take a look at the machine, if it's the temperature, if it's hot or cold service. So that is for machinery that is in use that you want to check. Pipe connections as well, are they bolted securely? And the mounting bolts, we have all 4 bolts as highlighted there. There's the skid securely bolted to the foundation, and then the coupling. Does it have wear? Does it need to be replaced? So these are some checks, general condition checks you want to do. Realignment checks continuing the foundation. This is like for a new installation, or if it's stable, it's level, it's flat, it's clean, and you want to clean up and around the machinery feet. So we see the base there, the skid, and then we see an image. That's a flat image. We have a level, and then we have a mirror. So flatness, when you speak of flatness, we're speaking of a geometric condition in which there's little irregularities. So we don't want a base that's bowed. So it's bowed, neither does it have a crown, like if it's a turtle back. You want it flat within specifications. Level, when you speak of level, you speak of a geometric condition that is in a horizontal plane to the Earth's surface. So that's why we talk about level. And then the mirror there, how does the mirror fit in? Well, that just to show that something can be flat, but not necessarily level in terms of what we are speaking about. So when you speak about level, we speak about a geometric condition in the horizontal plane relative to the Earth's surface, right? So as the mirror shows, it could be flat, but not necessarily level. Some further pre-alignment checks, we're looking at a condition called soft foot. And if you picture a 4-legged chair where one foot is short, it gives a rocking motion. So that is what soft foot really describes. So is the machine standing stable on the foundation? So we're looking at 2007 inch. Anything more than that indicates soft foot. So the machine feet should all be in the same plane, resting on the foundation. So there are different types of soft foot. We have parallel soft foot, which is the first image on the first part of the composite image on the right. You have parallel soft foot where the whole machine foot is off the base. We have angular soft foot, which part of the machine foot is touching the base and part is open on top. Then you have squishy foot, which can be caused by corrosion as illustrated here, or having too many shims on the machine foot can cause squishy foot. And then we have soft foot from external forces, which typically is called pipe strain. Some persons consider pipe strain separate from soft foot. So where we have the discharge piping pulling the pump up off its base. So it creates a gap underneath the foot. So that's soft foot condition there as well. So all these are checks to do before actually starting the alignment process. So how do we correct soft foot? Well, with all the hold on bolts tightened, place a dial indicator on one of the foot pads as close to the bolt head as possible. Loosen the bolt and read the deflection as shown in the image. And measure deflection greater than 2007 inch should be shimmed. After shimming, tighten the bolt and move on to the next foot and repeat the procedure for all 4 feet. Or instead of using a dial indicator, you could use feeler gauges instead of the dial indicator. If you don't have feeler gauges, you could probably use shims. Laser alignment systems have a softfoot mode that can also be utilized. The thing to note with the laser alignment systems, they are actually measuring, because they will be located on the shafts of both machines, they'll be measuring the shaft deflection as you loosen and tighten the bolt. So while it gives an indication of possible softfoot, to truly measure softfoot, you need to be at the feet. So pre-alignment checks continue. We're looking at shims. We don't want to have more than 5 shims per foot. That will cause a squishy foot. So if you have quite a number of shims, what you can do is cut a piece of plate that will make up majority of the gap, and then we utilize shims to fill in the rest. So the shims, when utilizing the shims, are they clean from dirt and rust? Which material is it? Stainless steel, brass, or aluminum? So you want to have similar materials in terms of the shim. The most popular shim material is stainless steel. Jack and bolts, pre-alignment checks. Do we have jack and bolts? These are very useful for the persons doing the alignment. If you don't have jack and bolts at your machine, it makes it much more difficult for the person doing alignment. That increases the time to do the alignment. And so that's the first image on the right. The second image is a tool that can be purchased where this horizontal adjustment tool, it has a nut that goes over the bolt head, and it tightens on the foot of the machine and able to slide the machine from side to side. Pre-alignment checks continue. Runout. Runout is measured on the couplings or the shafts. Correcting excessive runout requires either replacing the defective coupling or the shaft. The max runout is 0.003 of an inch. So we place the dial indicator in any point in space. Then we rotate the shaft or the coupling, and looking at the total indicator runout of 0.003 of an inch. Anything more than that indicates you have excessive runout, which should be addressed. If it's not addressed, it will make the alignment process more difficult, and also will not, the machine condition will not be the best. So we are going into the methods of shaft alignment now. So some typical tools utilized for shaft alignment. We have tape measures, rulers, straight edges. A ruler could act as a straight edge. Micrometers, calipers, dial indicators, lasers, and detectors. Before we actually get into the different methods, we'll just be looking at three methods today. Just want to highlight this principle. Shaft alignment is based on circle mathematics and trigonometry. In pure horizontal misalignment, the measurements taken around the circumference or the face of a shaft define the shape of a perfect sine wave. In pure vertical misalignment, the measurements will define the shape of a cosine wave. For all practical purposes, a misalignment condition where the shafts are misaligned both vertically and horizontally will produce a sine wave with an offset in the neutral axis and an angular lag in the waveform. So here we have the neutral axis. We have our measurements with a dial indicator or laser, and you see this shape here. It looks like a a sine wave, but is not a pure sine wave. Right? Of course, with a pure sine wave, you have a positive going peak, and then you'll go through the change at the neutral axis, and then you have a negative going peak, and it ends at 360 degrees. This information proves useful in the case of, especially with laser alignment systems. You may know that some systems have the ability to measure with limited shaft rotation. So probably 40 degrees or 60 degrees. And it's because of this principle that they're able to basically generate the rest of the sine wave so that they could make the alignment correction identified to the user. Right? So continuing. So you're looking at the reverse indicator method now. It's best suited when the distances between the measuring points of each shaft range from 3 inches to 30 inches. The procedure, well, we attach the alignment bracket or brackets firmly to one or both shafts and position the indicator on the perimeter of the other shaft or the coupling hub. This can be done with one indicator or both indicators as shown, which is typically done as shown in the image here. We zero the indicators at the 12 o'clock position. Then we slowly rotate the shaft and bracket arrangement through 90-degree intervals, stopping at the 3, 6, and 9 o'clock position, and we record each reading either plus or minus. Just to note, 3, 6, and 9, these positions, they are determined at looking from the driver, for example, the motor, along the train to the driven machine. So if we at the non-drive end of the motor and we're looking along the train and we picture the face of a clock, on top will be 12 o'clock, to the right will be 3 o'clock, the bottom will be 6 o'clock, and to the left will be 9 o'clock. And then we record each reading as a dial indicator traverses along the circumference of the shaft. When the needle or the stem, when the stem gets pushed in, it goes positive, and when it comes out, it goes negative. So depending on where you stop 3, 6, 9, the reading could either be positive or negative. So continue with the procedure. We return to the 12 o'clock position to see if the indicators read 0. If the indicators don't read 0, that means we have a problem that should be investigated. Probably the brackets were loose or not secure to the shafts. So we repeat steps 2 to 4 to verify the first set of readings, and then if one bracket was used, we mount the bracket on the other shaft and repeat these steps 1 through 5. So here's a little mathematics that describe the position to adjust the equipment using the reverse indicator, where we have distances A, B, C, D, and E. A refers to the distance between the driver feet, the motor in this case, the front foot and the back foot. Then B describes from the front foot to the point where the dial indicator is on the driver shaft. Then we have C, which is the distance between both indicators. D, the distance between the indicator on the driven shaft to the front of the driven machine. And then E, the distance between the feet of the driven equipment. And a note, as mentioned here, when you take any reading on the rim of a coupling hub, that value you get from rotating from the top to the bottom, you should halve that value. Why? Because when a dial indicator measures from the top to the bottom, is actually measuring twice. It's measuring the gap the offset twice, on top and on the bottom. So you need to half the value you get on the dial indicator. So what are the advantages of the reverse indicator method? Well, it's typically more accurate than the rim and face method, as the distance from the mounting point on the bracket to the point where the indicators capture the readings on the shafts is usually greater than the distance a face reading can be taken. If the, just give me and get some water here. Sorry about that. Okay. So it's typically more accurate than the rim and face method, because the distance between where the brackets are located is greater than the distance a face reading can be taken. If the machinery is supported by sliding type bearings, that's journal bearings, and the shafts are floating back and forth axially, when rotating the shaft to capture readings, there's virtually no effect on the accuracy of the readings. The disadvantage, both shafts must be rotated. It's difficult to visualize the position of the shafts from the dial indicator readings, and bracket sag must be measured and compensated for. So we come out to the rim and face method. So as you see in our image, one indicator is on the rim, or the circumference of the coupling hub. The other is on the face. So we're going to attach your bracket to one shaft and position the indicators on the face and the diametrical surface of the other shaft, or the coupling hub. We zero the indicator at the 12 o'clock position. We slowly rotate the shaft and bracket arrangement through 90-degree intervals, stopping at 3, 6, and 9 o'clock positions, and we record each reading, plus or minus. So looking at our image here, we see the face readings on the inside of the circle, and then the rim readings on the outside. They have top, bottom, north, and south. That's the labeling you utilize in this image. So return to the 12 o'clock position to see if the indicators read zero. If they don't read zero, that means a possible issue with the bracketing or the surface of the coupling hub. We repeat steps through 2 through to 4 to verify the full set of readings. So we have some math here again as well in determining the outer position, the equipment. So we have the distance between the motor feet, the distance from the first foot, the motor foot, or the driver foot to where the bracket is located. Then we have the distance C between where the bracket is secured to where it measures on the rim. We have D between where the bracket where the dial indicator is on the rim to the first foot of the driven machine, and then we have the distance between both feet in the driven machine, right? So we have our little formulas here to help us through with the mathematics. So advantages of the rim and face method. This is a good technique to use in situations where one of the machinery shafts cannot be rotated, or it will be difficult to rotate one of the machinery shafts. The rim, or the diametrical surface of the dial indicator, shows the center line offset or parallel misalignment, and the phase indicator indicates that an angular misalignment condition is present. This is a good method to use when the phase readings can be taken on a large diameter, typically 8 inches or greater. This method begins to approach the accuracy of the reverse indicator method whenever the diameter of the phase readings equals or exceeds the span from the bracket location to the point where the rim indicator readings are being captured in the reverse indicator method. So basically what it's saying is if the span between the reverse indicator method, if the phase reading is equal or greater that span, it begins to approach the accuracy of the reverse indicator method. Some disadvantages is not as accurate as the reverse indicator method if both shafts can be rotated, and particularly if the phase measurements are taken on diameters less than 8 inches. If the machinery shafts are supported in sliding, plane, or sleeve bearings, it is easy to actually float the shafts toward or away from each other when rotating the shafts, resulting in bad or inaccurate phase readings. And bracket sag must be measured and compensated for. So you mentioned in both the reverse indicator and the Raman phase, this concept of bracket sag or indicator sag. So how do we deal with that? Well, if we're using a dial indicator for alignment, you need to determine the difference between the reading taken on the 12 o'clock position on top compared to when it is on the 6 o'clock position at the bottom. The difference in these readings is a result of gravity deflecting the indicator bracket away from the shaft. It is reading in the bottom position. It is not necessary to eliminate sag, but to know what it is and to adjust it in your final alignment readings. So we have this method. So what you do, rigidly mount the indicator bracket on a rigid piece of pipe with the dial indicator stem resting in the 12 o'clock position, as seen in the top image to the right. In this position, set the indicator at 0 and then roll the pipe until the indicator is at the bottom 6 o'clock position on the pipe. In the example shown in the bottom, the indicator sag was measured at negative 5,007 inch. And this value will be added to the value that you get in measuring either reverse indicator or Raman phase. So we come now to the laser detector method of shaft alignment. In laser shaft alignment, the detector has a position-sensitive device called a PSD. The PSD outputs a varying electric current based on the laser striking within its active surface area. We can see that on the image to the right. As the laser traverses the area of the PSD, a variation in current occurs, and this variation is converted to a distance measurement. When the shafts are rotated, if the center lines are collinear, the output current from the detectors do not change. However, if the center lines of rotation are not collinear, the laser draws a circle or an ellipse onto the detector's targets. And based on the system configuration, one detector measures the offset and the other measures the angle, or both detectors measure both the offset and the angle. So that's basically whatever alignment system, that's basically how it works, right? The laser draws a circle or an ellipse. Of course, a circle is just a special form of an ellipse. So what are the typical laser alignment systems? Well, we have a single laser mounted on a shaft projects a beam to a roof prism, which is mounted on the other shaft. So the laser will be mounted on the stationary machine, most likely the pump. The beam is reflected 180 degrees and is observed by the PSD. The beam is centered in the 12 o'clock position by sliding the roof prism up and down on the support rods and angled horizontally to have the reflected beam strike in the center of the PSD. So we see that from the images to the right, where we have the single laser with the roof prism. And you see, if we strip it down to its bare bones, as it were, we have a laser detector on one unit, and then we have the roof prism reflects the beam back to the laser detector system. We have a beam splitter now. A single laser is projected to a beam splitter where some of the light passes straight through to one PSD and the rest is reflected to the other PSD. So the rotor line utilizes this piece of technology where it splits the beam. Come now to dual laser systems. So one laser detector assembly is mounted on the shaft with the laser up and the detector down. The other laser detector assembly is mounted on the other shaft with the laser down and the detector up. Each beam is centered in the opposing position-sensitive device PSD by pitching each laser up or down and side to side with adjustment screws. So we have typical manufacturers of dual laser detector systems presented here. So the procedure, similar. So I won't go through that in terms of the distances. And then it's similar as well, where we attach the brackets and then the zero the lasers and so forth. Right? So advantages of laser and detector systems. They're fast and accurate. They're quick to set up, easy to use, highly reliable. The possibility to generate reports with results straight away, easy to learn and to use, the possibility to measure with a small shaft rotation, such as 40 degrees, elimination of bending of hardware and setup mistakes. Then the speed and precision saves you money, a disciplined and repeatable process, and reduce energy consumption utilizing laser detector systems. Disadvantages, well, they are relatively expensive compared to dial indicator systems. The range of measurement is somewhat limited because many manufacturers use 20 millimeters by 30 millimeters detectors. Some systems do offer range extension capabilities. Is incapable of measuring runout conditions because it is not measuring the actual shaft, unlike a dial indicator will measure the shaft. So it's possible to align bent shaft and not know it. Sometimes it's difficult to capture readings in bright sunlight or well-lit areas. Accuracy potentially reduced in the presence of excessive steam or heat, or if the lens are dirty. And calibration suggested on an annual or biennial basis. So let's have this case study now. So it involves a horizontal split case pump. This pump is typically used in chill water systems or fire water systems. So we did the pre-alignment checks. We checked softwood using both the laser alignment system as well as feeder gauge, right? So typically it's done on just one machine, the driver. We did it on both machines here. And you can see the top image being the motor and the bottom image being the pump. Another pre-alignment check was pipe strain. Note as the displacement here. And here the blue and the black. See the vertical and horizontal. So this displacement was when we loosened the discharge piping. And then we have this lull here because we didn't take off the system. And so we left it on, and then we loosened the suction. So you see the flexion there as well, the displacement, right? So you have both the suction and the discharge piping. When we loosen both, we see the displacement, right? The pipe strain. So there's the setup, the measurement setup. So starting on top, we have the distances between the feet of the driver, the motor. So that's MF1, MF2, which was 14.5 inches. From machine foot to the M sensor was 12 inches. The distance between the S and the M sensors was 7 inches. The M sensor here and the S sensor here. And the distance from the S sensor to the center of the coupling was 3.5 inches. We have some machine data here. It was a motor to a pump. They had 2 pair of feet. These were not utilized here, lock feet. This is for base bong or bolt bong conditions, and we didn't save it, the software measurement here. Thermal compensation, well, that wasn't considered, neither utilized. And then you have the tolerance. So here we use the offset at angularity. The offset was 2 tau, 2,000th of an inch or 2 mils, and the angle was 2 tau per inch. Right? So here we have the ASFONG values. Note that these values is here you have the vertical result on top, the horizontal result below. You see the offset for the vertical was off, and this is at the coupling, right? These values are at the coupling. And then the horizontal, the offset is off as well. Note the MF1 and the MF2. This is the foot values. So we measure at the coupling, but we make the machinery movement, the adjustment at the feet. So this is what was required to bring it within tolerance. So there's the ASLEF values showing an intolerance condition. Everything is green and okay. So you know the values 0.7 minus 0.7. All of these are less than the 2 tau per inch, which was the tolerance set. And that's basically it. So thank you so very much for listening. And we have our Q&A now.
Thank you, Engineer Vidal, for that wonderful presentation, man. Very informative. You highlight a lot of key points. You know, one of the key things I take away from that and that resonate with me is the pre-alignment checks. You know, a lot of these pre-alignment checks, people you know, look past, and has a lot. They present themselves with a lot of challenges within the alignment process, and they tend to go in circles. You know, a lot of the like the software checks, the base flatness and all that, the the run out especially. And once you don't correct these things, you go in circles and you have a very difficult time with the alignment. So that I found was very important and informative as well. The progression of the different alignment methods was also a nice point that they illustrate there. A lot of the younger generation must want to know what you're talking about. What is reverse dial, right? You know, we don't we never use that method. We don't know what that is. We know about using that laser receiver, right? And having the alignment program, you know, suggest movements and all these things. So it was nice that they went back to the fundamentals of that. So with that being said, you know, we'd like to entertain any questions that the guys may have. They could either type it in, use the hand raise icon. We will call out there, and you could, you know, voice your question to Engineer Vidal if you wish to do so. So we'd like to entertain any questions now. If by chance we're not getting any questions, we will Engineer Lester and I will have to take your guys' places, take your places to ask Engineer Vidal list of questions to foster the discussion. So we like to entertain any questions anyone might have right now.
Okay, we have one question from Engineer Kamal Singh. It's in the chat. Define the differences between trial and error and precision alignment methods?
Trial and error and precision. Well, the name alone suggested trial and error. I guess the name alone suggests the issue. Trial and error. I'm not sure exactly what it means by that, but so with alignment, you could start with the very simple, just using a straight edge. And that will give you a certain level of accuracy. Then you use the dial indicator, which improves the accuracy of the straight edge. And then you have the laser alignment system, which improves the accuracy of both the dial indicator and the straight edge. So the laser alignment system is the most accurate. So that will be the precision alignment method. The trial and error is just that you just trying out stuff to see what happens, you know. So you could be eyeballing it, seeing if it look all right, they're looking like it aligned, you know. So, but I'm not too sure exactly what they meant by trial and error, but that's the progression of alignment systems.
Okay. Engineer Kamal Singh, did he address your question or your concern?
Yeah, when I said trial and error, I really just meant starting from straight edge, feeler gauge, taper gauge as
Okay.
the starting point.
I thought that is what he meant.
Yeah.
Straight edge. Yeah.
Yeah. So they still have the value. Of course, the name of the webinar was an introduction, right? So we couldn't cover everything with shaft alignment, but we use the straight edge and so forth to do like we call rough alignment. So we utilize that especially with laser alignment systems. Based on the laser alignment system, you have you only have a certain measurement range. So you use the rough alignment methods with taper, feeler gauge, straight edge to bring the couplings as close as possible within the measuring range of the laser alignment system. And then you can use the laser alignment system to continue the alignment.
Okay. Thanks, Kamil.
We have Engineer Daryl Rampasad with a question. You could take the floor.
Good night, everyone. It's not really much of a question, it's more of a comment. This introductory course, this introductory webinar was very informative. I am a junior engineer now starting off in the field, and it was very informative. I'd like to commend Engineer Lyndon for breaking it down simple so that everyone could understand. And it was very educational. I mean, I saw and have experience in doing this job, and knowing the theory now behind it just made you understand more, okay, so why we doing it, the purpose of doing it, and you have better understanding that. So I commend Lyndon, Engineer Lyndon, on this.
Yeah, you could comment, Lyndon. No problem with that.
Thank you very much. Thank you very much, Daryl, for your feedback. Much more reason to become a member of APET for these type of sessions and these type of learning sessions where knowledge is shared.
Yes, so working on the application.
No problem. We have a question from Kevin. It's in the chat. Are there measuring methods that can continually record alignment before wear or that can minimize repair failure damage? So by that, I am probably thinking he's talking about a live monitoring system. What do you think, Lyndon and Christopher?
Yeah, well, you're thinking much better than me. I was wondering where I was going, but it makes sense what you're saying.
Yeah.
So yeah, there are systems where you could mount laser detectors on the drive and the driven machine, and as such they will measure from run up, from start to run up, to measure the displacement horizontally and vertically. And you could use that information now to do even precision alignment, in the sense that a machine might be operating in a hot environment, so it may thermally grow. So while you measure it offline to actually measure the displacement, and then you could input those values in your alignment system now to have accurate shaft alignment. I'm not sure if that answers Kevin's question.
It looked like Engineer Kevin got bumped off, but I do agree with what you are saying, Engineer Lyndon, because I've seen systems like on steam turbines or turbines where they're not sure of the thermal growth values and they use the live monitoring systems. I think I could definitely concur that the Proof Technique system has that capability, where you have special brackets and you could monitor the thermal growth from shutdown to startup. And you could input those values within your alignment correction. So I do agree with what you are saying. It's whether Engineer Kevin, if his question was answered. Engineer Kevin, do you mind speaking? All right, well, until he feels is able to speak, we will take Engineer Akil Ali.
Hey, good.
Your hand was
Thanks
raised.
all.
Yeah, good day, good day.
Yes,
Nice
good
to
night,
have you
all.
here.
Yeah, firstly, Engineer Linda, let me apologize for joining a bit late. Joining right at the point in time where you're going through the reverse dial method, and Engineer Christopher would have made the comments. You know, the younger ones among us, we know it in theory, but you know, probably never executed it in the field. So, in terms of the laser systems being, you know, more accurate, maybe faster to use, any specific scenarios in the field you might want to use reverse dial over precision or laser?
I would say no, but there may be some purists, some reverse indicator purists who may say yes. But the
Okay.
to me, I think the lasers,
Yeah.
the capability of laser systems now, you know, there's a lot of things they can do which the reverse indicator method will not be able to do. So
Okay. Yeah, it was just a question out of curiosity. So that's basically it from me.
I think the most I
Thank
could
you.
say is that, like for example, and then the point you brought up about some of the advantages and disadvantages, you know, run out measurements is one of them. You're really using a dial indicator for run out measurements, and you really can't depend fully on the laser for that, right? You know, you have some drawbacks there. So I would say that for the most part, that probably the area where I see might have depend on a dial indicator as opposed to a laser, you know. But other than that,
but that's using dial indicator to measure the runout. But in terms of the alignment, you mentioned your reverse indicator.
Yeah. So respect to our pre-alignment check, because they have like for example, the Softfoot Wizard for laser, the laser alignment methods and all that. No, some people would rather go directly with the dial indicator on the legs and trust that reading more than the laser, you know.
Yeah.
So pre-alignment check wise, probably the dial indicator, you know. Yeah.
Are there any more questions from the fellow engineers? Because I have one or a few, because I took my notes. I took my notes. So I will go last, and I will allow engineer Nisha that is to take the floor.
Okay, good night, everybody. My question
Good
is,
night, good night.
what are
Good
the
night.
parameters when doing alignment? Well, you have when you're hot alignment, what's the parameters, the difference doing a hot alignment and a cold alignment? You know, well, there's thermal growth, but what are I don't know if you could elaborate a bit on it.
By parameters, you mean what specifically? What you're looking at? Because, for example, when you say hot alignment, is it really hot alignment? Because by the time you
Okay, like
switch off the machine, then you have to lock out, tag out.
so
yeah.
what I was more talking about, okay, so you do like you have a boiler feed pump. So you'll do like a cold alignment first and do your checks. And then you will run your machine or heat it up to your temperature. So what the parameters between the cold alignment and your hot alignment after you run your machine?
We're looking at the thermal growth. Really and truly, I know the hot alignment, the quote-unquote hot alignment is something which some plants and individuals use. Generally is kind of discouraged because of one is not really a true hot alignment. As I mentioned before, by the time you switch off the machine, you lock out, tag out, and then you make the situation safe for the person doing the alignment. Then the measuring instruments, they could possibly be damaged by the heat of the shaft, so it won't really be a true quote-unquote hot alignment. What I could suggest is one, actually measuring the thermal growth as discussed before with a laser alignment system, where you have your brackets mounted on the machines outside of the shaft, and they could monitor it from either from startup all up to running speed, or from running speed all the way to shutdown. Outside of that, what some plants or individuals do, they try to get the material which the shafts are made of, and they calculate the thermal growth. So that's really a kind of hit and miss with that, but it's a method. I guess something is better than nothing. So those two methods I could think of offhand. I'm not sure if they answer your question.
Okay, thanks a lot. Yes, it did.
Engineer Lyndon, I have a question. This is our scenario, right? With regards to your pre-alignment checks, right? So you do your software checks, right? And let's say off of one or two legs, you catch a software of more than 5 tau or 5 mils, and you ignore it. You choose not to correct it. In your experience with excessive software, what type of challenges would you encounter in that correction procedure?
Well, we have a gap of 5 to 5 mils. So that means the person who the techs, when they torque down the machine foot, that will distort the case of the machine. So it's possible with that excessive strain on the machine foot, you could actually crack it or break it. That's one. You distort the casing, so the bearings will not be in a true concentric position. So you could find where the bearings they are. So you might eventually develop probably looseness between the outer race of the bearing and the housing of the equipment, be it the motor or the pump. So that's at least two areas it could, possible issues it could because of excessive sulfur.
Okay. Christopher,
so that distortion will cause like somewhat of a preloaded condition on the bearing. Is what you're saying?
Yeah.
Mm-hmm.
And in addition, you have an internal misalignment as well. So
Right.
the two between the outboard and the inboard, they will not be concentric. And that, for example, in the case of a motor, that will affect the air gap. So
Right.
Yes, sir.
So that's a possible problem there with that.
So with regards to confirming or diagnosing misalignment, right? Let's say ignorant vibration, right? What are your thoughts on possibly using, if your coupling guard allows it, right? Where there's a inspection hatch. What are your thoughts on possibly using a strobe to monitor visually monitor the coupling condition? Do you think that's a effective strategy for diagnosing misalignment?
Yeah, you could possibly see if we have some distortion of the flexible elements. You may see probably some material that break off on the ground. If it's a shimpack, this type of coupling, you may probably see cracks in the shims. So that's an excellent way of doing a check on the run to see if you have a issue with alignment.
Okay.
That same alignment book you reference and some of your material in the presentation there. If it's the same handbook thinking about, from what I recall, they had a lot of different cases of misalignment with different coupling types, right? And the signatures that come with it, vibration signatures that come with it. I know some maintenance professional might rely on vibration signatures to give them an indication of severity of alignment, which would prove to be the wrong approach, because it actually have cases where it was severely misaligned and the vibration signatures did not correlate well, right? Or the vibration amplitudes did not correlate well with the state of misalignment that they actually had. And it's only when the coupling element shared is when the vibration levels went up. So, that was an important point that you brought up, because you did mention the most effective way is to really make a sweep and really make a check to find out what kind of severity of alignment or misalignment that we're dealing with. Because it really can't always depend on the vibration signatures, So that was an important point.
Yeah, so that's why I highlighted the phase. The phase to me is more a better way than actually looking at the spectrum. But the thing is, because you're working with a tolerance, so you can see the phase is 180 degrees plus or minus 30. But is the equipment still within tolerance? The vibration won't be able to tell you that.
Right.
So it may have a residual misalignment, but it may be within tolerance. Just like you may have with unbalance, you may have residual unbalance, but it's still within acceptable, values. So.
Engineer Lyndon, you just sparked a nice flame there, because I think we had to bring you back to go through what is phase analysis and how to measure it, and a technical session on field balancing, because you're just swinging two easy topics there. So I think next year we have you busy. We had to have you busy with two interesting topics there.
Yeah, well, I'll try to make myself available. I know there are other competent professionals in the field as well. You could rely upon.
We could balance it out. Yeah,
Or you give yourself more work. Easy.
Yeah, yeah, give it. You're swinging two nice little terms there, and some people might know what you're talking about. So it's nice to clear the air. So with that being said, with softwood, right? So let's say you have a gearbox and you are seeing physically that the wear patterns on the gear are pointing towards gear misalignment. And you are seeing bearing wear, right? So there's filings at the bottom of the box, brass, right? So the brass is more like coming from the cage of the bearings in that said gearbox, right? You make a sweep and you see there that the shaft alignment good. Shaft to shaft, it's good, right? Is it safe to say possibly that gearbox is probably distorted due to softwood? Because how you mentioned that with the bearing housing, it could be out of wrong, and due to that distortion, that could possibly misalign your gears because of the softwood. Do you think that's a possibility in your experience, your thoughts?
Me or me not. Typically, gearbox cases are pretty solid, heavy. So if it's a lighter gearbox, possibly. And we have other things that may lean towards the gear misalignment.
So you're probably thinking installation procedures on whatnot.
Yeah.
All right, yeah. All right. We have engineer Yoko in Windsor. Or our regular. Yes, engineer Yokin, you have the floor.
Good night, team. Sorry for the late arrivals.
Good night.
A little crazy out here. But just you asked about this software being an issue, right? Particularly with split case gearboxes, we've had past where we did get some distortion when we did run-out checks between the bearing areas, right? And that actually contributed to the gearbox having a softwood. So after we did that alignment, we had to turn the gearbox on the side and check the base for that softwood. And it directly contributed couple tau as the case may be. So while it is far-fetched because most of these gearboxes are very rigid, it is possible that the softwood is a direct result of the gearbox being distorted.
Yeah, thanks. Thanks for your input, Wilkin. So it's about learning as well. These are webinars, so we have experiences from a diverse group of professionals that would like to share their input as regards, so one of the things I mentioned earlier with the pre-alignment checks is the condition of the foundation, right? So that as well could influence, how the machinery, for example, like gearbox always, has it begun to degrade over time? For example, a concrete base, so all these things kind of contribute to the condition.
We have a question from Kevin, engineer Kevin. He's from Tin Linden. So Kevin, you have the floor. You are free to speak. Okay then. You could type if you want. Okay then. Are there any more questions from the crowd, from the audience? Feel free to ask. And here in Appet, there's no Mr. Yoquin again. You go ahead, take the floor.
Yes, so I missed a good portion of the presentation, but I came in just to hear about there being out around. Is there tolerance range in terms of like bearing area being out around that will contribute significantly to vibration or the gearbox and such? Because I've experienced where we scrap down a gearbox and we have to do run-out checks throughout, and we'll have like a what we will call an egg shape on the bearing area, right? Either vertically or horizontally, and let's say it might be a 1 tower egg shape or 2 tower egg shape, and the client will not choose to remachine the bearing area so it to be fully concentric. Is that solely because they don't want to spend the money on it, or is it that, okay, a 1 tower, 2 tower, how much ever is allowable for the operation of the gearbox to not contribute to vibration and such?
Well, I can't determine what the client think in that circumstance, but if the fit is not a proper fit, you will see it in the vibration data. Typically looseness, it'll be bouncing in the bearing will be bouncing in the housing, so we'll have the ISO standard with tolerances and fits. I don't have that information with me. So
now, the next question is, how will that outer rung affect the effectiveness of the alignment that being carried out in terms of, okay, so we have misalignment and we have to adjust. Will it make it more difficult to adjust, knowing that there is that outer rung in the equipment, the bearing areas and such?
that is a good question. I would say it should, because you'll have too much tolerance in the bearing housing. So depending on how you do the alignment, if you do it with the coupling engage or disengage, uncouple alignment, but in any condition, once the bearing housing is not the proper fit, remember at the end of the day, sorry I missed the start of the presentation, but we discussed why we go through the alignment procedure. So you want to reduce leakage, damage to seals, bearings, shafts, couplings. So if you start off with a negative, as it were, things won't get better, right? So you'll be aligning in a bad position, and that won't make it better. So you won't align and correct itself. You'll just continue getting worse. Also.
Okay.
We have a question from Engineer Nisha.
Okay, from your experience, could you highlight on some tips when doing the alignment to bring it closer to precision tolerance? Like from your experience in doing alignment.
Well, the alignment procedure, we went through the methods. We have your pre-alignment checks, your softwood, then you utilize shims. So normally we typically use pre-cut shims, but you could also have shim stock material, and you could cut the shims accordingly. Typically, I do alignment with the coupling engage the coupling insert there. But there's a school of thought that it's better to do it uncoupled, where you actually see the shafts, the true shaft position, right? Because with it engaged, it could possibly be, as I mentioned before, aligning with a bent shaft. No, but so we use hydraulic pumps and rams. We use Bigfoot or crowbars to lift the equipment. If we have chain blocks, if we can utilize chain blocks, we use that as well. So all these are different tools to help do the lifting and the pushing because basically, as mentioned earlier in the presentation, we're dealing with horizontal deviation and a vertical deviation. So to address it vertically, we need to lift the machine to slip in the shims to make up the height, and horizontally we need to adjust the machine to push it. If there are adjustment bolts, we utilize that. If not, we try to utilize other tools to move the machine horizontally. So those are some of these things from my experience to utilize to get the required tolerance.
Thank you, Engineer Lyndon. Engineer Nisha, did that address your concern?
Yes.
All right. Thank you very much. We have a question.
I see Kevin here talk about wind turbines.
Yeah.
No, I don't have any experience with wind turbines.
But
who knows what the future holds, right? Who knows?
But he asked one before. He
asked
two
tolerance on the foot.
Two tolerance on the foot. How can it be achieved when there are lots of external vibrations, I assume?
Well, that case you had to use feeler gauge. The laser alignment system won't be too unless making a plug here for one system I utilize, right? The easy laser, there's a vibration filter. So you could adjust the vibration filter to try to contact the outside vibration. But typically a laser alignment system with lot of vibrations, you won't get an accurate measure. So you could use like the feeler gauge to help you there.
We have Engineer Yoquin with a question.
Mr. Earlier question is just to supplement Lyndon's previous response to Engineer Nisha. I am one person who has seen Lyndon in action firsthand, frontline over the years. And I know she was asking about tips. I don't know if she would have mentioned it in his procedure and pre-checks, but one of the things that has made Lyndon so successful is he facilitates as found checks, right? And with those as found checks, before equipment is taken down to work on and such, he is able to pick up quickly how much deviation or to anticipate that deviation so that when the equipment is to be installed and commissioned, he already has that information on how much he may need to, as we say, shim and such, to make the alignment easier, because Lyndon does alignment very quickly because he's well prepared. So after saying Lyndon, I'm not sure if you mentioned that before, but this is something I know about you, and it functions proper.
Yeah, thanks, Joakim, for the endorsement. I see, Bansi.
This is past president Bansi.
Okay.
What he's asking is in the instant of only replacing half of the coupling, what are the challenges you could encounter in conducting the alignment correction?
Thanks, past president Bansi. I don't know why would someone replace half of a coupling though. I don't. But that is a way of doing the uncouple alignment I mentioned. You use half a coupling and you have it loose. Dollars, yeah, dollars. That could be the only reason why, why would someone do half a coupling? Because half a coupling, remember the coupling, the other half that remains, it would have, remember we mentioned earlier in the presentation how the coupling it deals with the forces, the wear between both machines to accommodate the alignment conditions. So that half a coupling that remains would have already dealt with forces and wear on don't know how long, be it months, years. So to only replace half a coupling, you're looking for a failure sometime in the future.
Trouble. Yes. So are there any more questions from the audience? Engineer Gunai.
Kevin want to know when would the recording be available for later access?
My divisional PRO, which is Ezekiel, he will send me by latest tomorrow, he will send me the YouTube link and I shall distribute it to the entire mechanical engineer membership. So for sure tomorrow you all will get it because it's been recorded. So for sure you will get it. That's no problem. With that being said, are there any more questions from the audience? Engineer Gunai, you're looking like your brain is bubbling. Nah, you're good to go.
Engineer Vidal, are you aware of like some called target values and what are they as it pertains to alignment? There's something called target values. I believe something that the OEM does provide.
Well, to me, target values, I may be corrected, but to me, target values are basically the tolerance, really. Our OEM may have custom tolerances that they want their equipment to work under. So they supply those values, be it for thermal growth or whatever. So the person doing the alignment or the team, whoever doing the alignment, they need to work with what, at least if the client wants the alignment done to those values.
Right.
It could be for whatever reason they may want the alignment done to other values. So that's a decision for the client to make.
Yeah, I believe the OEM will present these target values as their personal specification to probably compensate for any thermal growth or anything like that.
Yeah, probably as well. Over the years, they probably have built up a library, a catalog, and these values have worked well for them. Probably for issues of warranty, they wanted a line to those values. So they have their reasons why they choose those values. But yeah, to me, that's my understanding of the target values. I may be wrong, but that's my understanding. It's basically tolerances, but specified by the OEM or the client.
Yeah. Look, you can have an next question here. Where do you go?
Engineer Yukun.
Hey, Lyndon, did you touch on cold alignment and hot alignment? And also, I just have a scenario that I needed some guidance on. So I did an alignment on a ship engine a while back. And it was a corrective because the vendor that installed and commissioned the engine did an alignment, and after the alignment, they welded brackets to hold that engine in place. And obviously, well, when we came, the alignment was off by 100 37 thou, but they were adamant that those brackets they welded kept it in place. What are your thoughts on that?
Just repeat that. I miss. Is it a ship, is that?
Yes. Alignment of an alternator to ship engine. And the vendor that installed and commissioned the alternator, they did the alignment and they welded prefab brackets on the four corners to hold the engine's alignment in place. About a week after, the client called and said, listen, the alignment is off. So we went to correct it. It was 137 thou off in the front and a couple hundred to the back. What are your thoughts on that scenario? Because the vendor were adamant that they computed the alignment within the tolerance set.
That's a good thing, man. I really can't speak on why the vendor would have done that.
Yeah.
Why they would
So
have done
that. We actually had a debate because the vendor is from the States and well, we do things properly and this, that, the other, but clearly the alignment was off. So we had to line out the brackets, we do the alignment, fill back fresh bolt holes, bolt down, double check, and everything was fine after that. But have you ever encountered using prefab brackets as a standard to lock down an equipment after alignment?
No. I've always seen hold-on bolts, either that or adjustable chocks.
Yes.
I've never seen it actually like welded down and held down thing. So that probably was their QA. QC that they did a good alignment, they welded down and they say, well, yeah, good.
That sounds like a ratch. That sounds like a ratch.
But I can't say why they will do that, because the nature of alignment is that over time you can't expect some movement, so you'll need to realign sometime in the future. And I don't know why they will weld it down.
So engineer, you can
those were not all of us. Yes.
Those were the coupling values or the leg values that you called out?
Both. There was 137 toward the coupling, and on the back leg, something like almost 300 towers.
And that was those type of Vulcan couplings?
Yes.
Oh. All right.
I know I've seen alignment work where they fabricate brackets. Now I assume the brackets that you're talking about is support brackets, or is it prefab brackets to contain the laser and receiver? Is it what we're talking about?
It was prefab brackets to position in place of hold-on bolts.
Yeah.
Because they were at the four legs.
Okay. I sure I know Linden Karate there's sometimes you have fabrication work, and when you have any kind of welding and induce heat, that kind of distortion sometimes could cause induce misalignment as a result.
Well,
so I'm not sure if that may be the case. In that case,
I absolutely agree with you, but this is something that I'm saying is supposed to be understood if we are all aligned professionals.
Right. Agreed, yeah.
And especially coming from an international vendor.
Yeah. I don't know why.
That's an interesting case study. I
don't know why they would do that.
Yes.
Yeah.
Engineer Yogan, that's it. That's it for him. With regards to the audience, no more questions. We would like to release Engineer Linden right now in good faith.
Yeah. So I just want to thank everyone for being present and participating, if not audibly, at least mentally. And as mentioned, with the title is an introduction to sharp alignment of horizontal rotating machines, right? It wouldn't be possible to cover everything, but I hope that what was presented will help you. I had some questions to ask. I didn't forget to ask you questions, right? So I hope that what was presented will help you if you either perform an alignment for yourself or you oversee a contractor or service provider who does alignment for you, that you could have an understanding what the service provider or the contractor is doing. And you can ask questions if you think things are not proceeding as you think it should. So I hope the presentation was helpful, and continue to be part of the space here that Engineer Lester and his team is they're really working hard in providing relevant mechanical issues for the engineering community locally.
Engineer Stephen Tornell, you're very lucky. You're very lucky. Like I know you. We will slip you in just for one more. We will slip you in just for one more. Go ahead, take the floor.
Good night, tonight. I know it said in that introduction, would you be calling back to do advanced alignment techniques like multiple trains, alignments, those kind of stuff?
Stephen, you hear any break up, boy? I don't hear any clear at all.
What I got from his question, or the remnants of it, is that this is he understands this is an introductory alignment presentation, but he is asking, in the near future, would you be doing advanced techniques or presentation on advanced alignment techniques? Would that be possible?
Well, normally alignment course is a 3-day, sometimes 4-day course. So it's not really possible. The most we could do is introductions, right? With the time.
Yes, totally agreed.
And yeah. So
totally agreed. But Engineer Tornell, we will put some thoughts into that, and probably we could develop a workshop session. If the populace does agree to it, we could entertain that and we could make that an event for sure.
All right.
Right. So no problem. Anything for you. So with that being said, right, the Appet Mechanical Division would like to release Engineer Lyndon in good faith, and thank you very much for this voluntary act. It was well received, very knowledgeable. I gained a lot of knowledge. Thank you very much for sharing your experiences and for answering all these different questions to the best of your ability. We really appreciate it. Thank you very much. So
yes,
hope to have you back. And thank you very much. Great job.
Yeah, no problem. If anyone wants the presentation, they could reach out to Lester, and I could share the presentation with you. Right? There's no
problem.
Proprietary information here, so
for sure, the recording will be shared. If any of you wants the soft copy presentation, Engineer Lyndon, as mentioned, is willing to share it. No problem. Thanks a lot, Lyndon. Thanks for your service.
Okay, thanks again.
Yeah. Thank you very much, Christopher, and thank you very much, all you fellow engineers. See you guys early next year. Enjoy the season.
All right, later.
Good night, guys.
Fantastic, man. Blessings, everyone.